All right, welcome back, and we're now ready to start section 9.7 on eigenvalues and eigenvectors. This section has been talked about a couple times. I kept saying, yeah, when we get to section 9.7, we're going to learn a nice way of finding the steady state vector, and the method that we're going to use is via these things called eigenvalues and eigenvectors. But eigenvalues and eigenvectors, as we're going to see, is a vast, vast subject with many applications and beyond just solving that probability stuff. And we're going to see a couple of the applications in this section, namely a nice way of taking powers of a matrix, and of course, finding the steady state vector for a transition matrix. So let's start with the following example. Consider the matrix A equals 1, 1, negative 2, 4. Just a good old-fashioned matrix, 2 by 2. And what happens if I apply that matrix to the vector or the column matrix 1, 2? What happens if I do that? Well, let's calculate it. This is a 2 by 2 times a 2 by 1, so it produces a 2 by 1. And at this point, hopefully you're proficient enough with multiplication of matrices to see that it becomes 3 and it becomes 6. Hopefully you see that. Now, if you just stop here, there's really nothing special about this. It's just, okay, matrix times a vector gives me a vector. We've done this 1,000 times. But notice how if I factor out a 3, I'm left with 3 times the original vector that I began with. In other words, A times the vector V, or the column matrix V, equals a constant, and it's traditional to use the Greek letter lambda, times the same vector V. This equation, AV equals lambda V, is the central equation of this chapter. Essentially, if all you're given is a matrix A, our goal is to find V and find lambda, that A times V equals lambda times V. The V is called the eigenvector of the matrix, and lambda is called the eigenvalue, or A eigenvector and A eigenvalue, because as we're going to see, matrices can have more than one. Again, we are looking to satisfy this equation where all you're given is A. Here's a matrix. Find me its eigenvectors, find me its eigenvalues. That's the goal. In the example that we did, I demonstrated that the vector 1, 2 was an eigenvector with an eigenvalue of 3, but I didn't show how to find it. Are there any other eigenvectors? Well, what happens if I take the same 1, 1, negative 2, 4, and this time I apply it to the vector 1, 1. Let's see what happens here. If I apply it to 1, 1, I get 2, 2. In other words, I get 2 times the vector 1, 1. So we see that not only is the vector 1, 2 an eigenvector of this matrix, the vector 1, 1 is also an eigenvector. The eigenvector and eigenvalues in the first case are 1, 2, and 3. And in this case, it's 1, 1, and 2. Different eigenvalues, different eigenvectors. Just so you don't think that anything works, let's just try a random vector. How about 2, 1? 1, 2 worked, so let's try 2, 1. And what do we get? We get 3, 0, which is not equal to a constant times the original vector. So 2, 1 is not an eigenvector. In general, a 2 by 2 matrix is going to have a maximum of 2 eigenvectors and a maximum of 2 eigenvalues. 3 by 3, 3, 4 by 4, 4, 5 by 5, 5, and so on. But in general, you can never have more eigenvalues and eigenvectors than the size of the matrix. In this case, 2 by 2 gives me a maximum of 2. So now the question is, how do I find the eigenvalues and eigenvectors? All you're given is A. And the answer is as follows. I'm going to rearrange AV equals lambda V. It's the same thing as saying AV minus lambda V is equal to 0 by subtracting lambda V on both sides. Now, I would like to factor out the V, but there's one problem. This equation makes no sense because A is a matrix and lambda is a number. And you can't subtract a number from a matrix. You can only subtract a matrix from a matrix. So we're going to throw in an intermediate step where I put in the identity matrix of the appropriate dimension. I know that the identity times V is just V, so mathematically that's okay. And now I can factor out V, and that gives me A minus lambda I times V is equal to 0. Now, obviously, hopefully it's obvious, that V equals 0 works. A times 0 equals lambda times 0. If you multiply a matrix times the 0 vector, 0, 0, or 0, 0, 0, depending on the size, and you multiply a constant scalar, lambda, times the same 0, 0, in both cases you get zeros. So zeros are kind of boring. They don't really give us anything interesting. So we're going to just ignore them. We're going to say, yes, 0 works, but let's ignore that one. Let's find something else. So the goal here is to find something other than the 0 vector that works. Now, if the inverse of A minus lambda I exists, as complicated as A minus lambda I looks, it's just a matrix. If its inverse exists, then I can multiply both sides by the inverse, and I arrive at that V is equal to 0. On the left, the inverse cancels. I'm left with just V. On the right, the inverse times 0 is just 0. Boring. If the inverse exists, V equals 0 is the only vector that works, is the only solution. So I don't want that. I want something besides 0. So I need A minus lambda I inverse to not exist. Now, do I have a condition on a matrix for when its inverse exists or not exists? And the answer is yes. The determinant of a matrix will tell me whether or not its inverse exists. In fact, if the determinant is 0, the inverse does not exist. So I need A minus lambda I, the determinant of A minus lambda I, to be equal to 0. This is the condition that I will use in order to find the eigenvalues. Notice that V is gone. There's no V in this equation. Determinant of A minus lambda I is equal to 0. It allows me to solve for the lambda. So when you're given a matrix and you're said, hey, let's find the eigenvalues and eigenvectors, you say, no problem, eigenvalues come first. So the determinant of A minus lambda I equals 0, the solutions of that will give me the eigenvalues. This is called the characteristic equation. So if it ever says, hey, what's the characteristic equation? It's the determinant of A minus lambda I is equal to 0. Now, we're going to algebraically rewrite that, but essentially that's what it is. So let's go ahead and do an example that demonstrates finding the eigenvalues and then how to find the eigenvectors from there. So let the matrix A be 0, 1, 3, negative 2. We are going to find this matrix, we're going to find its eigenvalues. How are we going to do that? Well, we start with the equation. What is the determinant of A minus lambda I? this is a determinant of A, which is 0, 1, 3, negative 2, minus lambda times the appropriate sized identity matrix. So this becomes the determinant of 0 minus lambda, 1 minus 0, 3 minus 0, negative 2 minus lambda. Now, notice that all you need to do is subtract lambda along the main diagonal and leave the off diagonal elements the same. So 0 and 2, subtract lambda, 0 minus lambda, negative 2 minus lambda, 0, negative 2. And then 1 and 3, leave them alone. So you don't got to write these lines. You can go directly to it. Subtract lambda along the main diagonal, leave the off diagonals alone, and we want this to be equal to 0. Well, what is the determinant of a 2 by 2 matrix? Well, I know how to find that. I multiply the two elements along the main diagonal. So negative lambda times negative 2 minus lambda, minus, I multiply the two elements along the other diagonal, set it equal to 0. So I get lambda squared plus 2 lambda minus 3 is equal to 0. This is the characteristic equation. It is the equation that the eigenvalues must satisfy. Well, luckily in this case, it's factorable. I get lambda plus 3, lambda minus 1 equals 0. So I get lambda equals negative 3 and 1. These are the two eigenvalues of the original matrix. Now, next question is, once I have the eigenvalues of the matrix, how do I go ahead and find the eigenvectors? So for that, we're going to go back to this equation right here. Now that I have my eigenvalues, I go one step back up to the previous, I went through all this work to get to lambda, so we're working back up. This is the previous equation, and I'm going to plug in the lambdas and solve for v. A minus lambda I times v is equal to 0. A minus lambda I v is equal to 0. And we're going to do this for each lambda. So let's do it for lambda equals negative 3. And then we'll do it for lambda is equal to 1. So for negative 3, when I go to a minus lambda I, again, this is a minus lambda I here, which means this is a minus lambda I here. All I need to do is plug in negative 3 into that one. So I get negative of negative 3, 1, 3. Negative 2 minus negative 3, that's negative 2 plus 3 is 1, times the vector v is equal to the vector 0. Of course, I want to solve for v, so rather than writing it as just v, I'm going to write it as xy, where I want each of x and each of y, and since it's equal to the vector 0, I will write it as the vector 0, 0. Now you'll notice if you write out the equations here that you get, on top I get 3x plus y is equal to 0. And on bottom I also get 3x plus y is equal to 0. And that's always going to be the case when you're dealing with eigenvectors, that the last line of your matrix is always going to be redundant. So if it's a 2 by 2 matrix, I just look at the first line. If it's a 3 by 3 matrix, I look at the first 2 lines. If it's a 4 by 4 matrix, the first 3 lines, and so on. The last one is always going to be redundant. So all I get is 3x plus y equals 0. And then all you need to do here is just find an xy that makes that work. And the easiest one that I can think of is letting x be 1 and y being negative 3. If x is 1 and y is negative 3, you get 3 plus negative 3 equals 0. That makes it a true statement. I have not only the eigenvalue, but I have its eigenvector. Now you might say, well, wait a second. I was thinking of using, for example, 2, negative 6. I won't say this is equal, but what if I used 2, negative 6 instead? That also works. And the answer is yes, it does also work, and it's perfectly valid. When you solve for an eigenvector, any non-zero multiple of that will also be an eigenvector. I can multiply by 3, by 7, by -2, by 16. Knock yourself out. They all work. But why not just take the easiest, so at least in my mind, what the easiest is, and the easiest here is just 1, -3, so we'll use that one. For the other one, lambda equals 1, I go back up here. Remember, this is my a minus lambda I. So -1, 1, 3, -2 minus 1, -3, times the currently unknown xy is equal to 0, 0. First line gives me -x plus y is equal to 0. Second line, by the way, gives me 3x minus 3y is equal to 0, which gets me to the same place. If I divide by 3 or by -3, again, it's going to be redundant. So what is it's the simplest vector to use. Why don't we take x to be 1, and why don't we take y to be 1? -1 plus 1 is sure enough is equal to 0. So we have our 2 eigenvalues, and we have the 2 eigenvectors that go along with them. Now that we have that down, let's jump ahead to exercise 9I and do some problems involving eigenvalues and eigenvectors before jumping into the second half of this section, which talks about some of the applications. So question number 1. It says, determine the characteristic of each matrix in the form lambda squared plus p lambda plus q equals 0, and then determine its eigenvalues. So essentially the goal is, what are the eigenvalues? So part A, we have the matrix A is equal to -4, -2, 3, 1. So we're going to first subtract lambda along the main diagonal and keep the off diagonal elements the same. And then we're going to take its determinant. So -4 minus lambda times 1 minus lambda minus -6, set it equal to 0. Multiply this out. I get lambda squared. Minus lambda plus 4 lambda becomes plus 3 lambda. Minus 4 plus 6 becomes plus 2 is equal to 0. And this is factorable into lambda plus 2. Lambda plus 1 is equal to 0. By the way, this is the characteristic equation that you're after. It's in the form lambda squared plus p lambda plus q is equal to 0. Like the question asked, in this case, p is 3 and q is 2. And what are my eigenvalues? My eigenvalues are -2 and -1. Part B gives me matrix B, which is 5, 0, -3, -5. Again, as always, you should be pausing and doing this yourself. First thing we're going to do is subtract lambda along the main diagonal. Then we are going to take its determinant, 5 minus lambda, -5 minus lambda minus 0 is equal to 0. Then we're going to write it out. Lambda squared minus 25 is equal to 0. This is the characteristic equation where p is 0 and q is -25. And then I can go right ahead and solve it. And I go, in this case, lambda is equal to plus or minus 5. So there are 2 eigenvalues. And then for part C, we have that the matrix C is equal to -2, 1, -1, 2. So if I subtract lambda along the main diagonal, I get that. Take its determinants, -2 minus lambda, 2 minus lambda, minus -1, set it equal to 0. Multiply it out, lambda squared plus 2 lambda minus 2 lambda goes away, minus 4 plus 1 minus 3 is equal to 0. And that's the characteristic equation. And what are my solutions? Add 3 to both sides, take the square root of both sides, and you get plus or minus the square root of 3. Nothing says the eigenvalues have to be nice numbers. They can be radicals, positives, negatives. They can be imaginary. In fact, I think it will be a great IA topic to talk about matrices, eigenvectors, eigenvalues, what conditions you need on a matrix for its eigenvalues to be real versus imaginary, which is extremely important in quantum mechanics, where the matrices represent real world measurements, in the sense that the eigenvalues are your solutions, are what come out of the measurements, and you can't have imaginary solutions. It makes no sense. It's a cornerstone of quantum mechanics. A lot of advanced stuff, a lot of fun for those who find any of this fun. All right, question 2. It says, determine whether or not is lambda equal -1 an eigenvalue of 3, 2, 3, 8. And as always, you should be pausing, trying to solve this. So there's 2 ways to attack this. One is to directly check whether -1 is an eigenvalue, which would entail needing to know the eigenvector, or at least finding an eigenvector. And the other is just what we just did a few minutes ago, which is let's just find the eigenvalues and then see, is -1 one of them? Well, if I subtract lambda along the main diagonal and keep the off diagonal elements the same, and then I take its determinant, which is 3 minus lambda, 8 minus lambda minus 6, set it equal to 0. That gives me lambda squared minus 11 lambda plus 18 is equal to 0, which when I factor, gives me lambda minus 9, lambda minus 2 is equal to 0, which tells me that lambda is equal to 2 and 9, not -1. So therefore, the answer is a big resounding no. -1 is not one of the eigenvalues, because we found the eigenvalues and -1 was not on the list. There are no other ones. Question 3. Find the eigenvalues and eigenvectors of each matrix. So now we have a little more work. There's 5 of them here, A, B, C, D, E. What are the eigenvalues? What are the eigenvectors? C equals 5, -8, 2, -3. Start by doing what? Subtracting lambda along the main diagonal. Then by doing what? Taking its determinants, 5 minus lambda, -3 minus lambda, minus -16, setting that equal to 0. Next is to put it in the right form, which is lambda squared plus 3 lambda minus 5 lambda is minus 2 lambda, minus 15 plus 16 is plus 1 is equal to 0. Then it's to factor, and in this case, it's a perfect square. Lambda minus 1 squared is equal to 0. So in this case, we get only one eigenvalue, not 2. Every eigenvalue brings at least one eigenvector along with it, possibly more. So let's see how many eigenvectors we get from this one eigenvalue. So lambda equal 1. We do 5 minus lambda, -8, 2, -3 minus lambda, times the unknown vector xy equals 0, 0. First line, 4x minus 8y is equal to 0. I can always simplify by dividing by 4. X minus 2y is equal to 0. And then I just need to know an eigenvector that satisfies this. Why don't we take x to be 2 and y to be 1? One eigenvector, not 2, just 1. So this particular matrix only has one eigenvalue, and therefore, and also one eigenvector. Big question. How do you know when a matrix has more than one eigenvalue, or only one eigenvalue, or any eigenvalues? There are matrices that have none, or at least no real eigenvalues. So there's a lot of stuff going on here behind the scenes. The book does not really cover it. It just gives you a little bit, kind of whet your appetite, and then hopefully you go on, take Calculus 1, Calculus 2, Calculus 3, a course in advanced math to prepare you for how to think mathematically, and then linear algebra, which is what this stuff's all about. All right, let's go to part B, which is next matrix. Q is equal to 2, 4, 5, 3. Let's start by subtracting lambda along the main diagonal. then by taking the determinant, which is 2 minus lambda, 3 minus lambda minus 20, set it equal to 0. Multiplying it out, 11 lambda squared minus 5 lambda, 6 minus 14 is equal to 0. Hopefully this is factorable. I really don't want to use the quadratic formula if I don't have to. Lambda minus 7, lambda plus 2 is equal to 0. So I get lambda equals -2 and 7. Hey, 2 eigenvalues. So let's do them. Which is the one for lambda equals 2 and which is the one for 7? Well, let's plug in -2 for lambda. 2 minus -2, 4, 4, 5. 3 minus -2, 5. On the unknown vector xy gives me 0, 0. 4x plus 4y equals 0. Second one's redundant. Divide by 4, so x plus y equals 0. And the easiest is 1, -1. What about 7? Well, 2 minus 7, -5, 4, 5, 3 minus 7, -4. Acting on the unknown xy is equal to 0, 0. -5x plus 4y is equal to 0. So what do I get? The easiest one is x equals 4, y equals 5. -20 plus 20 is equal to 0. So 2 eigenvalues, 2 eigenvectors. Next one, C. Oh, this is an interesting one. It says I equals 1, 0, 0, 1. Now, this one, actually, we don't have to go through everything. We could, and there's nothing wrong with it. But let's think about it. We know that I acting on any vector just gives me that vector back. It's the identity matrix that acts on a vector gives you the vector back. In other words, IV is equal to 1v for all vectors. No matter what vector you give me, they're all eigenvectors. Everything's an eigenvector with eigenvalue 1. Now, if you did it by this process, subtract lambda along the main diagonal, take the determinant, set it equal to 0, you get exactly the same thing. So what are the eigenvectors? So the answer is the eigenvectors are everything. Everything's an eigenvector. But if I just pick one, like for example, 1, 0, that is an eigenvector, 100%. However, if you have a 2 by 2 matrix, we would really like, and when I say like, as we're going to see in the next portion of this section, we really want to have 2 eigenvectors. A 2 by 2 matrix, we really want to have 2 eigenvectors. But we don't want a multiple of the first one. I don't want to give me 2, 0 or 3, 0 or 4, 0 because those are all just the same as the first. So I will take 0, 1 as my second. 1, 0, 0, 1. These are not multiples of each other, so they are what are called independent vectors, technically linearly independent vectors. And because I want 2 eigenvectors, I know I'm done. You might say, well, maybe there's a third one. Well, if you think of it about it, let's say I said, oh, 4, 5. That's one also. Well, if you think about 4, 5, you can actually write that as a combination of the 2 that I gave you already. 4, 5 is 4 times 1, 0 plus 5 times 0, 1, which means these 2 here can get anything else. No matter what you give me, 17, -2, no problem. 17 times 1, 0, minus 2 times 0, 1. Hey, I got it. So 1, 0 and 0, 1 get me everything. And because they get me everything, I don't need anything else. So I can only have 2 eigenvectors, and these are them. This was a special problem. I would not expect something like this because there's nothing else that has the same results, at least at this level. Okay. In fact, even in the book, it says, here's an exam hint. In an exam, matrices will always have distinct real eigenvalues. So you don't got to worry about a double eigenvalue, like 1 having multiple eigenvectors, and you don't got to worry about imaginary either. So the book might give you 1 or 2 just because it wants to broaden your depth, but you don't have to worry about that on the exam. Now the next one is actually really interesting. No, not this one. The next one after this will be really interesting. This one, just another example. So we have the matrix P, which is 0, -3, 3, 0. So what are we going to do? Well, as always, we are going to subtract lambda along the main diagonal and leave the other ones alone. And then we'll take the determinant, which is lambda squared minus 9, negative lambda, that's lambda squared, -3 is 9, minus 9 equals 0, which gives me plus or minus 3. Good. 2 eigenvalues. Love it. Let's try -3 first, and then we'll try 3 after. We want both the eigenvectors. For -3, 0 minus -3 is 3, -3, -3, 3. Acting on the unknown xy gives me 0, 0. First line, 3x minus 3y is equal to 0. That's the same thing as saying x minus y is equal to 0. Whoops. So I get 1, 1 as my eigenvector. The other one, 3, I get -3, -3, -3, -3. Acting on xy is equal to 0, 0. So -3x minus 3y is equal to 0. -x minus y is equal to 0. So here I'll get 1 and -1. 2 eigenvalues, 2 eigenvectors, and we're done. Now, the next one is a little bit connected to the previous section, because we have the matrix T, they're calling it, 0.4, 0.7, 0.6, 0.3. How is this connected? Because this is a transition matrix. Notice that the probabilities, the numbers, they add to 1. And none of them are 0. They're all positive. So this is a regular transition probability matrix. And we already know that there exists, or we want the steady state vector, right? This was a problem for the previous section. What is a steady state vector of a matrix, of a transition probability matrix? And the answer is, wait a second. If you look at this equation, this is nothing more than saying, what is the eigenvector associated with an eigenvalue of 1? So all we got to do now is find the eigenvector associated with 1, and we have the steady state vector. Of course, from a problem solving standpoint, we're not going to do anything any different. We subtract lambda along the main diagonal. We then take the determinant, 0.4 minus lambda, 0.3 minus lambda, minus 0.42 is equal to 0. That gives me lambda squared minus 0.7 lambda plus 0.12 minus 0.3 is equal to 0. And I know this is factorable because I already know that one of the eigenvalues must be 1. If I didn't know it, I can use the quadratic formula or something like that. I can even multiply by 10 to get rid of the decimals. There's multiple ways of doing this, but as a mathematician, what you want to do is you want to be able to spot shortcuts rather than just doing the same work every single time. So if lambda minus 1 works, this one has to be lambda plus 0.3. Let's check. Lambda squared, yes. 1 lambda minus 0.3 lambda is minus 1 lambda plus 0.3 lambda is minus 0.7 lambda. Hey, it all works. So we get lambda equals 1 and negative 0.3. I always like to do them from more negative to more positive. So let's do lambda equals negative 0.3 first. 0.4 minus negative 0.3 is 0.7, 0.7, 0.6. And since it has to be redundant, this better be 0.6, and it is. Acting on xy is equal to 0, 0. So I get 0.7x plus 0.7y is equal to 0, which is the same thing as x plus y is equal to 0. So that gives me 1, negative 1 as the eigenvector. But it's the other eigenvector that I really care about, because this is the one that is the steady state vector. So negative 0.6, 0.7, 0.6, and negative 0.7. Yeah, 0.3 minus 1, negative 0.7, acting on the unknown vector xy equals 0, 0. So negative 0.6x plus 0.7y is equal to 0. Decimals are annoying. Let's multiply by 10. Negative 6x plus 7y is equal to 0. So what can I get? Well, I can make x be 7 and y be 6. So 7, 6 would be the steady state vector for this original matrix. It's always nice to check. I didn't check any of the others, but because this one has application to what we did before, let's go ahead and check. 0.4, 0.7, 0.6, 0.3, acting on 7, 6. 0.4 times 7 is 2.8. 2.8 and 4.2 gives me 7. 0.42 and 0.18 gives me 6. Sure enough, it does work. Of course, if you trust the math, then you kind of know that it works. Question 4. It says, here's another transition matrix, T equals, but this one does not tell me what A and B are. It just gives me the matrix. A and B are some numbers, and of course, 1 minus A and 1 minus B are beneath them because it has to add to 1 each column. It says where 0 is less than or equal to A less than or equal to 1, and 0 is less than or equal to B less than or equal to 1. If there are probabilities, they have to be between 0 and 1. I really honestly believe that this is a mistake, and it should be 0 is less than A, which is less than 1, and 0 less than B, which is less than 1, and not have the equal signs there. I can check later. Because if probabilities are 1, then there's not really the chance of switching states sometimes, which makes problems a little more trivial and less requiring the need of all this math. So we're going to go with 0 less than A less than 1, 0 less than B less than 1. Part A says, show that lambda equal 1 is an eigenvalue, and then determine the other eigenvalue. Well, no problem. We know how to do this. Subtract lambda along the main diagonal, leave the off diagonal alone. And then we take the determinant, which is A minus lambda times 1 minus B minus lambda minus B times 1 minus A, set it equal to 0. Now, let's multiply it out in combined terms. We get A minus AB minus A lambda minus lambda plus B lambda plus lambda squared minus B plus AB is equal to 0. I do get some nice minus AB plus AB goes away. And what am I left with? I have a lambda squared. And then I have some lambdas. I'm going to combine them together into B minus A minus 1 lambda. And that takes care of those 3 terms. B lambda minus A lambda minus 1 lambda. Lambda squared is already taken care of. Plus what's left, A minus B equal to 0. This is my characteristic equation. It's a quadratic. So let's use the quadratic formula. Actually, I don't even have to. They told me that 1's an eigenvalue. So that means I know that if I try to factor it, I'll have a lambda minus 1. And then it's lambda minus the other eigenvalue is equal to 0. Well, this one has to be A minus B. Because when I multiply it out, minus 1 times minus the thing at the end has to give me that guy right there, A minus B. Let's check to see this works. Lambda squared, yes. Minus 1 lambda, minus A lambda plus B lambda, yes. And then plus A minus B. Beautiful. So what do we get? We get lambda equals 1, and lambda is equal to A minus B. And then part B says, determine the eigenvectors for each one. So first let's do lambda equals 1, and then we'll do lambda equals a minus b. So for lambda equals 1, we plug in on top a minus lambda, that's a minus 1, b, 1 minus a, 1 minus b minus 1, that's negative b. Acting on x, y gives me 0, 0. So I have a minus 1x plus by is equal to 0. So what can I use for my x, y? Well, b could be x, or x could be b, and y could be 1 minus a. So then I get, a minus 1 times b, and b times 1 minus a, which is the reverse, sure enough adds to 0. Okay, the other one, a minus the object a minus b gives me b, 1 minus a, 1 minus b minus a minus b gives me 1 minus a, as it should, x, y equals 0, 0. Bx plus by equals 0. Same thing as saying x plus y is equal to 0. And I already know this one, it's 1, negative 1. So those are my two eigenvectors that go along with these eigenvalues. All right, fun stuff. So now we move on to what is called diagonalization. Diagonalization. The idea of diagonalization is taking a matrix and rewriting it in a way that makes the matrix diagonal. What does diagonal mean? Numbers could be here, but zeros are everywhere else. In the case of a 2 by 2 matrix, a diagonal matrix would have whatever numbers there, maybe 0, maybe not, zeros off the main diagonal. If it's 3 by 3, same idea. Diagonalizing a matrix means I don't care what these numbers are as long as the numbers off the main diagonal are 0. Now you can't just take a matrix and just erase numbers and make them zeros. So the process is very, very specific. And as an example, we're going to use the matrix A equals 5, negative 3, negative 6, 2. And we want to diagonalize this matrix. How do we do it? It's not a one-line process. This just takes a few lines of work. The start is the same way for everything else in this section. Let's find the eigenvalues and then use them to find the eigenvectors. So how do I find the eigenvalues? Subtract lambda along the main diagonal. Then take the determinant. So 5 minus lambda times 2 minus lambda minus 18 is equal to 0. Lambda squared minus 7 lambda minus 8 is equal to 0. Lambda minus 8, lambda plus 1 is equal to 0. So I get lambda is equal to negative 1 or 8. Okay, so I have my two eigenvalues, negative 1 and 8. Now let's find the eigenvectors. Well, let's do lambda equals negative 1 first, and then we'll do lambda is equal to 8. With lambda equals negative 1, 5 minus negative 1 is 6, negative 3, negative 6, 2 minus negative 1 is 3. Acting on x, y gives me 0, 0. 6x minus 3y is equal to 0, divided by 3. 2x minus y is equal to 0. What's the simplest one that satisfies that? X equals 1, y equals 2. So 1, 2. And at 8, we get 5 minus 8, negative 3, negative 3, negative 6, negative 6. Acting on x, y is equal to 0, 0. Negative 3x minus 3y is equal to 0. X plus y is equal to 0. So that gives me 1, negative 1. So I have my two eigenvalues and I have my two eigenvectors. Now, let P, this is a new matrix now, let P equal a matrix whose columns are the eigenvectors. So the first eigenvector was 1, 2. The second one was 1, negative 1. So we're going to make a matrix, a new matrix, whose columns are the eigenvectors 1, 2, 1, negative 1. And what we're going to do next is take the inverse of this matrix. How do I take the inverse of a matrix? You flop or switch the main diagonal elements. You negate the off diagonal elements, and then you divide by the determinant. Negative 1 minus 2, you divide by negative 3. So this gives you 1/3, 1/3, 2/3, negative 1/3. So we have P and we have P inverse. What do we do next? Well, watch this. What I want you to do is I want you to evaluate the following. I want you to evaluate P inverse AP. In other words, take that P inverse, which we just found, multiply it by A, which was the original matrix, 5, negative 3, negative 6, 2. And then multiply it by P. And let's see what we get. So when I do the first one, I get 5/3 minus 6/3, it's negative 1/3. Negative 1 plus 2/3 is negative 1/3. 10/3 plus 6/3, 10/3 is 16/3. And then negative 2 minus 2/3 should be negative 8/3. And then 1, 2, 1, negative 1. So I get negative 1/3. Uh-oh, did I make a mistake? I might have made a mistake. Let's do the math again. 5/3 minus 6/3 is negative 1/3. Negative 3/3 plus 2/3 is negative 1/3. 10/3 plus 6, 16/3, and negative 6 and negative, no, it should be good. So what am I getting here? Let me just check it in my calculator. So we're going to put in a 2x2 matrix. The 2x2 matrix is 1, 2, well, 1, 1, 2, negative 1. And then we're going to inverse that matrix, which is 1/3, 1/3, 2/3, and negative 1/3. And then multiply that by A, which is negative 1/3, negative 1/3, 16/3, negative 8/3. And then multiply it by the last one. So negative 1/3. Oh, bleh, dummy. Negative 1/3 minus 2/3 is negative 3/3, it's negative 1. And then negative 1/3 plus 1/3 is 0. And then 16/3 minus 16/3 is 0. And then 16/3 plus 8/3 is 24/3, which is 8. So what do we get when we multiply P inverse times A times P? We get a diagonal matrix. Now, this is not just any diagonal matrix, but look at what my eigenvalues were. My eigenvalues were negative 1 and 8. So this matrix that we get, which we'll use the letter D for, is a diagonal matrix, but it's the matrix of eigenvalues. And this is always true, assuming that you have two eigenvectors so that you can have a matrix of eigenvectors. You can always do this. You can always find a diagonal matrix which is related to the original matrix via the formula P inverse AP is equal to D, which is equivalent if you multiply on the left by P and on the right by P inverse, it's equal to P D P inverse. So the original matrix can be diagonalized by writing it as the matrix of eigenvectors times the matrix of eigenvalues times the inverse of the matrix of eigenvectors. We call this process diagonalizing the matrix. What's the purpose of it? Well, let's think about it. What's A squared? If you have a matrix and you square it, it's not always simple to find what the new matrix is going to be because you got to do the multiplication. But if I write it as PD P inverse times PD P inverse, because A squared is, that's what A is, then the P inverse and the P, when you multiply them together, it becomes the identity matrix, and you just get P D squared P inverse. And in general, A to the N is P D to the N P inverse. Now, why is taking the diagonal matrix to the nth power any better than taking the original matrix to the nth power? And the answer is because we know a trick for diagonal matrices to the nth power. Because of all the zeros, you can just take each entry to the nth power and not worry about the actual multiplication. This is a huge, huge result. Let's do an example to demonstrate its usefulness. A equals 1, 2, 3, 0. Essentially, the goal of this problem is to find A to the fourth power. Not really a question, just find A to the fourth power. Now, on paper 2, this is relatively easy. You plug in A into your calculator, you do it to the fourth power, you have your answer. But what if this is on paper 1? If it's on paper 1, then you got to do 1, 2, 3, 0 times 1, 2, 3, 0, get that matrix, times 1, 2, 3, 0, get that matrix, times 1, 2, 3, 0, get that matrix. Not too much work. It's only 3 multiplication problems. But what if it was A to the 14th power or to the 400th power instead? That would be a lot more work. So what's the shortcut? The shortcut is to recognize that A to the fourth power is P D to the fourth power P inverse. So if I can find P and D, then taking A to the fourth power is easy. So part A, diagonalize the matrix. That's first. How do I diagonalize the matrix? I write A as PD P inverse. Well, I can only do that if I have P, which is the matrix of eigenvectors, and D, which is the matrix of eigenvalues. So let's find the eigenvalues and eigenvectors like we've done before. We subtract the lambda along the main diagonal. We then take the determinant. Negative lambda times 1 minus lambda minus 6 is equal to 0. Lambda squared minus lambda minus 6 is equal to 0. Lambda minus 3, lambda plus 2 is equal to 0. Lambda is equal to negative 2 and 3. Okay, I now have my D matrix, negative 2 and 3 along the main diagonal, and zeros everywhere else. Great. What about my P matrix? Well, to do that, I need to know my eigenvectors. So we'll do lambda equals negative 2, and then we'll do lambda is equal to 3. When lambda is negative 2, 1 minus negative 2, I get 3, 2, 3, 2. Acting on x, y is equal to 0, 0. So I have 3x plus 2y is equal to 0. So what's the simplest one to use? 2, negative 3 would work. 6 minus 6, okay. And when lambda is equal to 3, 1 minus 3, negative 2, 2, 3, negative 3. Acting on x, y is equal to 0, 0. Negative 2x plus 2y is equal to 0. That's the same thing as saying negative x plus y is equal to 0. That gives me 1, 1. So at this point, I now know P. Now, here it's important. If your first eigenvalue is negative 2, then you better make sure that your first eigenvector is the one that's associated with negative 2. Second eigenvalue is 3, so your second eigenvector would be the eigenvector associated with 3. Because the book, for example, does it the other way. They did 3 first and negative 2 first, so the details of the math is a little different. But it's perfectly acceptable as long as you keep them straight. So what is P inverse now? Well, let's flip the main diagonal. Let's negate the off diagonal and then divide by the determinant. So it's 1/5, negative 1/5, 3/5, and 2/5. That's P inverse. Therefore, as a result, A equals to P D P inverse. 2, 1, negative 3, 1. D was negative 2, 0, 0, 3. And P inverse is 1/5, negative 1/5, 3/5, and 2/5. So that is part A, the diagonalization of A. Okay, now, what is part B? It says, what is A to the fourth? Well, A to the fourth then is 2, 1, negative 3, 1. Negative 2, 0, 0 to the 3 to the fourth. 1/5, negative 1/5, 3/5, and 2/5. And then part C says, fine, no problem. Find me A to the fourth, but no powers. No problema. Because I know how to do a diagonal matrix to the fourth power. That's negative 2 to the fourth power, 0, 0, 3 to the fourth power. And it just gives me this. Now, the problem ends here, but let's go ahead and just solve for this. So I get 32, 81, negative 48, 81. That was not horrible as a multiplication because it's diagonal. Made things really, really simple. Times, now what should I do here? Because I don't want to deal with fractions, I'm just going to pull out the 1/5. So that way I can avoid needing fractions. I should have done that earlier, but I didn't. So what do I have? I have 32 plus 81 times 3. That's 275. Negative 32 plus 81 times 2 is 130. Negative 48 plus 81 times 3 is 195. And then 48 plus 81 times 2 is 210, all times 1/5. 275 times 1/5 is 55. 130 times 1/5 is 26. 195 times 1/5 is 39. And 210 times 1/5 is 42. So that is A to the fourth power. And it didn't take me very long to do it, and most of the time I was spent explaining what I was doing. So when you get really proficient at this, you see it actually is really, really quick. Faster, I think, than actually multiplying A to the fourth power directly. Now, let's consider the following problem, which is an extension of what we did last sections with the transition matrices, but now incorporating this knowledge of eigenvalues and eigenvectors, and in particular, diagonalization. And we're going to see how it gives us another way of finding the steady state vector. So in this example, we have two neighborhoods, neighborhood A and neighborhood B. It says people are moving from one to the other, and each year, 8% of people currently in A move to B. So the probability of moving from A to B is 8%, 0.08. And 12% go from B to A, 0.12, which tells me that there's an 88% chance that people remain in B, and there's a 92% chance that people remain in A. This is our transition diagram. It also says you can assume that there's no other movement. So if people leave these two neighborhoods completely, other people come in and we just ignore them. So it says, so this was, it's been this way every year since 2015, 8% leave one, 12% leave the other. This is just, these are the numbers. And then it says, that the initial state vector, there's 24,500 people in A and 45,200 people in B. And the question essentially is, eventually, what are the numbers going to stabilize at? People are going to leave A, people are going to leave B, people are going to stay, people are going to stay. The numbers are going to keep changing. What does it stabilize at? So we know already from what we've done before that the transition matrix here, A to A is 0.92, and then of course 0.08 is A to B, and B to A is 0.12, and B to B is 0.88. So we want the steady state vector. Now, there's multiple ways of getting this. In the last section, we saw that we can solve a system of equations to get it. This time, we're going to do it a little bit differently. What we're going to do is we are going to diagonalize the matrix. Let's see what happens when we diagonalize the matrix. So I subtract lambda from my main diagonal, and I keep the off diagonal elements the same. And then I take the determinant of this, which is 0.92 minus lambda, 0.88 minus lambda, minus 0.08 times 0.12 is equal to 0. That gives me lambda squared. And I'm use my calculator here so I don't do anything really dumb. And that's minus 1.8 lambda minus 0.0096 is equal to 0. And there's a lot of decimals here. So let's use the quadratic formula. Lambda equals negative b plus or minus the square root of b squared minus 4 times negative 0.0096 for AC all over 2a. 1.8 squared plus 4 times 0.0096. If I take the square root of that, I do not get a nice number. Did I do something wrong? Because I should have nice numbers here. Let's take a look. 0.92 minus lambda, 0.88 minus lambda, 0.08 times 0.12. So lambda squared, it is minus 1.8 lambda, and it is 0.08 times 0.12. Oh, of course, of course. In fact, I don't need to do this at all. I did make a little tiny error because we all do that sometimes. It's a horrible thing. Well, lambda squared minus 1.8 lambda. I did the 0.08 times 0.12, but I missed the 0.92 times 0.88 minus 0.08 times 0.12. So it really should be plus 0.8 is equal to 0. And let's not forget, because it's a transition matrix, lambda equals 1 is always an eigenvalue. So it has to be lambda minus 1. Whoops, lambda minus 1. Lambda minus 0.8 is equal to 0. So we get lambda is equal to 1 and 0.8. Okay, we have our two eigenvalues. So let's do the eigenvectors now for each one. If I plug in 0.8, 0.92 minus 0.8 is 0.12, 0.12, 0.08, 0.08, acting on xy is equal to 0, 0. I immediately get 1, negative 1. And of lambda equals 1, I get negative 0.8, 0.12, positive 0.8, negative 0.12, acting on xy is equal to 0, 0. This one is not immediate, but negative 0.08x plus 0.12y is equal to 0. Multiply both by 100. Negative 8x plus 12y is equal to 0. Divide by 4. Negative 2x plus 3y is equal to 0. So I get 3, 2. So one is 1, negative 1, and the other one is 3, 2. Therefore, my P matrix is going to be 1, negative 1, 3, 2. My P inverse matrix, I flip those, I negate those, and I divide by 2 minus negative 3 by 5. So keeping the 1/5 out, I get that. And my D matrix is 0.8001. So as a result, my original T matrix, which was 0.92, 0.12, 0.08, 0.88 is equal to P, which is 1, -1, 3, 2, D, 0.8001 times P inverse, which is 2, -3, 1, 1 with a 1/5 constant, which the 1/5 you can put all the way in front at the end, doesn't really make a difference. So this is T. Now, we want the steady state vector. So in other words, let's think about it like this. If you keep transitioning over and over and over and over and over again, then what, I can form T squared, T cubed, T to the 4th, T to the 5th, but essentially what I'm looking for is T to the infinity. Now, T to the infinity is not really defined. What I mean by that is T to the N in the limits as N goes to infinity, a little calculus notation that we don't have to worry about, but it essentially means just as N gets really, really big, what does this approach? And the answer is actually, we know that from what we did in the last little part, this is still the limit as N goes to infinity technically. But what I can do is I could just raise the D to that power. Now, as N gets really, 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 really big, what happens to 0.8 to the N? Well, 0.8 squared, 0.8 cubed, 0.8 to the 4th, they get smaller. 0.8 squared is, for example, 0.64. It's smaller because it's a number between 0 and 1, technically -1 to 1. So as you raise it to higher and higher powers, it gets smaller. In the limit, it goes to 0. And what is 1 to the N? That's just going to remain 1. So I get 2, -3, 1, 1 with the constant 1/5. This I can multiply. First one gives me 0, 0, 3, 2. And then I have 2, -3, 1, 1 still with the constant of 1/5. And then when I multiply this out, I get 3, 2, 3, 2, still with a constant of 1/5. So I get 3/5, 2/5, 3/5, 2/5. Notice that the columns are the same. And we know the columns are going to be the same from what we did in the previous section. Not only that, this tells me that my steady state vector is going to be that same column, 3/5, 2/5. Let's check. If you take the original 0.92, 0.12, 0.08, 0.88 and act it on 0.6, 0.4, so 0.92 times 0.6 plus 0.12 times 0.4 gives me 0.6, and 0.08 times 0.88 plus, 0.08 times 0.6 plus 0.88 times 0.4 does in fact give me 0.4. So we see that the steady state probability vector is 3/5, 2/5. How do we incorporate that into my original state vector? Well, the total amount of people is 24,500 plus 45,200. So there's a total of 69,700 people, which means 3/5 of that will be an A. So steady state vector S infinity gives me 41,820 people in A, and the remaining 27,880 people are going to be in B. So we can use diagonalization to help us find the steady state probability vector, but also the steady state vector if we know the initial starting state. So with that under our belt, let's now jump ahead to exercise 9J. Question number 1. It says, here's a matrix R, -2, 1, 2, -3. And the eigenvalues are given as lambda1 equals -4 and lambda2 equals -1. And it says write R in the form R equals PDP inverse. Well, no problem. I have my D already, -4, 0, 0, -1. But I have to find my P, and I have to find my P inverse. To do that, we take lambda equals -4 and lambda equals -1. So it's -2 minus lambda, -2 minus -4, -2 plus 4 is 2, 1, 2, -3 minus -4 is 1. Acting on x, y gives me 0, 0. So 2x plus y is equal to 0. So the easiest way is x equals 1, y equals -2. And here I have -2 minus -1, -2 plus 1, -1, 1, 2, -2. Acting on x, y is equal to 0, 0. X plus y is equal to 0. Easiest 1, 1. So that means P is 1, -2, 1, 1. And P inverse is flip those, negate those, and then divide by the determinant, which is 1 minus -2. 1 plus 2 is 3. Therefore, the original vector R, a matrix R, -2, 1, 2, -3, is P D P inverse with the 1/3 that I threw in the front. 1/3 can go anywhere. It's just a constant. You can even multiply it out. You don't have to keep the constant out. It's just, I've come to realize that it's a lot easier. I make a lot less mistakes myself when I'm not dealing with fractions. Question number 2. It says, consider A equals 16, -35, 6, -13. It says A, determine the eigenvalues and eigenvectors of A, and then state why A is diagonalizable. So 16 minus lambda, -35, 6, -13 minus lambda. We get 16 minus lambda, -13 minus lambda, minus -35 times 6 is -210 is equal to 0. So lambda squared, 13 minus 3 lambda, and then -13 times 16 plus 210 gives me plus 2 is equal to 0. Oh, look at those small numbers. So I get lambda minus 2, lambda minus 1 is equal to 0. So lambda is equal to 1 and 2. So I have my eigenvalues. There's 2 of them. That means there must be 2 eigenvectors. If I have a column of eigenvectors, I know it's diagonalizable. That's how I know it. So lambda equals 1, lambda equals 2. When I plug in lambda, I get 15, -15, -35, 6, and 16 minus 1, -35, 6, and -13 minus 1 is -14. Yep, okay. Times xy is equal to 0, 0. So 15x minus 35y is equal to 0. Divide by 5. 3x, I can divide by more than 5. Yeah, no, divide by 5. 3x minus 7y is equal to 0. X is 7, y is 3 would work. And for 2, I get 14, -35, 6, and -15. X, y is equal to 0, 0. 14x minus 35y is equal to 0. Divide by 7. 2x minus 5y is equal to 0. So I get 5, 2. So I have the eigenvalues. I have my eigenvectors, right? Eigenvalue with its eigenvector, eigenvalue with its eigenvector. Why is it diagonalizable? Because I have 2 eigenvectors. B, express A in the form A equals PDP inverse. A, which is 16, negative 35, 6, negative 13, equals P, which is 7, 3, 5, 2. Those are my eigenvectors. D, which is 1, 0, 0, 2. P inverse. What is P inverse? I flop those, I negate those, and then I divide by the determinant, which is 14 minus 15, which is negative 1. Dividing by negative 1, the same thing by multiplying by negative 1, which means I can just change all the signs. So I get negative 2, 5, 3, negative 7. So that is part B. C. Find a general expression for a to the n. What is a to the n? Well, a to the n is p d to the n, p inverse. So that's just 7, 5, 3, 2. 1 to the n, which is 1, 0, 0, 2 to the n, negative 2, 5, 3, negative 7. D. Use your GDC. Use your expression in part C to find a to the 4. So a to the 4 is 7, 5, 3, 2, 1, 0, 0, 16, 2, 4, 8, 16, negative 2, 5, 3, negative 7. If we multiply the first two, I get 7, 3. And I get 80, 32 times negative 2, 5, 3, negative 7. And then if I multiply these, I get negative 14 plus 240, that's 226, the first one, and then 35 minus 7 times 80 is negative 525, and then negative 6 plus 96 gives me 90, and then 15 minus 7 times 32 gives me negative 209. And then it says confirm this with your GDC. So what I'm going to do is take out my calculator, edit a new 2x2 matrix of 16, negative 35, 6, and negative 13, and then take that matrix to the 4th power. And I sure enough get 226, negative 525, 90, negative 209. Whew! I would not want to have to go back and redo that one. Question number, that's not straight. Question number 3. Question number 3 says, consider the matrix T equals 0.4, 0.75, 0.6, 0.25. Ooh, we got a valid transition probability matrix. And so it says A, express T in the form T equals PDP inverse. Okay, well, we first got to find the eigenvalues. I know one of them is going to be 1. So it's going to be 0.4 minus lambda times 0.25 minus lambda minus 0.6 times 0.75 is equal to 0. Lambda squared minus 0.65 lambda, 0.4 times 0.25 minus 0.6 times 0.75 gives me minus 0.35 is equal to 0. I know one of them is 1, so the other one has to be positive 0.35. So I get lambda equals 1 and negative 0.35. Of course, negative 0.35, notice, is B minus A. Sorry, it's A minus B. So, you know, I mean, the chances of remembering this by the time the IB exams come around is nil to small. But one eigenvalue is A, and the other one is A minus B, 0.4 minus 0.75. But I wouldn't memorize that. I doubt even I'll memorize that. So I just know how to recreate it when the time comes. Now, of course, we need our eigenvectors. So we need lambda equals negative 0.35 and lambda equals 1. So 0.4 minus negative 0.35 is 0.75, 0.75, 0.6, 0.6, xy equals 0, 0. This is just 1, negative 1. and lambda equals 1 is negative 0.6, 0.75, positive 0.6, negative 0.75, x, y gives me 0, 0. So negative 0.6x plus 0.75 is equal to 0.75y is equal to 0, multiplied by 100. So negative 60x plus 75y is equal to 0, divided by 5. Negative 12x plus 15y is equal to 0, divided by 3. Negative 4x plus 5y is equal to 0. And this gives me 5, 4. So therefore, T, my original matrix, is P, 1, negative 1, and 5, 4. D, negative 0.35001 times P inverse. Flop those, negate those, and then divide by 4 minus negative 5. 4 plus 5 divided by 9, so we'll put a 1/9 in front. B, find T to the fourth using your answer in part A. So T to the fourth is 1/9, 1, 5, negative 1, 4. Negative 0.35 to the fourth, 0, 0, 1. And then 4, negative 5, 1, 1. And then verify your result using your GDC. So they actually want us to go through with this whole thing. So I'll keep the 1/9 for now. 0.35 to the fourth power is annoying. So I'm not even going to write it out. I'm just going to keep it as 0.35 to the fourth power. So I get 0.35 to the fourth power, negative 0.35 to the fourth power, 5, 4, 4, negative 5, 1, 1. And then what do I get? I get 4 times 0.35 to the fourth plus 5, negative 5 times 0.35 to the fourth plus 5, negative 4 times 0.35 to the fourth plus 4, and negative 5 times 0.35 to the fourth plus 4. So now that I have all that done, now 4 times 0.35 to the fourth plus 5, divide that by 9, I get 0.562225. Negative 5 times 0.35 to the fourth plus 5 divided by 9, I get 0.54721875. Negative 4 times 0.35 to the fourth power plus 4, all that divided by 9 gives me 0.437775. And negative 5 times 0.35 to the fourth power plus 4 divided by 9 gives me 0.43610763889. Of course, they probably just want me to round it to 3, but let's go ahead now and go back to the original one and edit a matrix. Put a 2x2 matrix in here of 0.4, 0.75, 0.6, 0.25, and then take this matrix and raise it to the fourth power. And I get 0.56225, 0.5472185, 0.437775, 0.4527, 0.4527. It gives me a different number down here. So I'm going to check my math. 5.45278125. Did I put it incorrect before? Maybe. I didn't think I did. I mean, they do have to add to 1, which they do. Negative 5 times 0.35 to the fourth plus 4 divided by 9. So did I make a mistake in the previous? Because everything else worked out great. It should be positive 5, not negative. 5 times 0.35 to the fourth plus 4 divided by 9, and that fixes everything. Yes, a negative times a negative is in fact a positive. I knew that. All right, part C. Using the long-term using the result from part B, determine the long-term behavior of t. So what is essentially t to the infinity? It's 1/9, 1/5, negative 1/4. Negative 0.35 to the fourth, it keeps getting smaller, so that goes to 0, 0, 0, 1, 4, negative 5, 1, 1. So keeping the 1/9, 0, 0, 5, 4, 4, negative 5, 1, 1. Keeping the 1/9, we get 5, 4, and then we get 5, 4. So 5/9, 5/9, 4/9, 4/9. So what is the long-term behavior of t? This is it. This is the long-term behavior. 5/9, 4/9, 5/9, 4/9. That's also the steady state vector, steady state probability vector. That 55%, 44% distribution would be the steady result. All right, awesome. And finally, the last question, question number 4. Says as follows. Suppose only 2 rival companies, R and S, manufacture a certain product. Each year, company R keeps 1/4 of its customers, while 3/4 of them switch. And each year, company S keeps 2/3 of its customers, while 1/3 of them switch. At the beginning of the year, 2005, company R had 6,500 customers, while company S had 5,200 customers. A, write down the transition matrix T, no problem. If we RS, R to R is 1/4 or 0.25, making R to S 0.75. S to R is 0.3 bar. Maybe fractions are better because we're going to have these. Bad decimals. So let's keep it as fractions. Okay, that's T. B. Find the distribution of the market after 2 years. After 2 years is just T squared times S0. So 1/4, 1/3, 3/4, 2/3 squared times 6,500, 5,200. Describe the change in this distribution from 2005. So it's after this, interestingly enough, that it wants you to write it as T equals P lambda P inverse. I'm not sure why they didn't do P dP inverse. It's got to be a mistake, another mistake. But we don't need it because we can just do this math. 1/4, 1/3, 3/4, 2/3, 1/4, 1/3, 3/4, 2/3, acting on 6,500, 5,200. So I get 1/16. Oh, let's just do my calculator. So 1/16 plus 1/4 gives me 0.3125. 1/12 plus 2/9 gives me 0.305 bar. 3/16 plus 0.5 gives me 0.6875. And the last one is 1/4 plus 4/9 gives me 0.694 bar, acting on 6,500, 5,200. So what does this give me? Well, times 59 plus this times that gives me about 3620 approximately. And I don't got to do the math on the other one because there's a total of 11,700. So if I just subtract off that, it gives me 8,080. So that is a distribution after 2 years, which means R dropped by Well, it was 6,500 and now it's 3,620. So R dropped by 2,880 and S went up. It was 5,200 and now it's 8,080. It went up by 20. Well, okay, I didn't need to do that, obviously. Okay, part C. Now it says, write T in the form P equals P lambda P inverse. I think it meant P T equals P dP inverse. I better have. So we know how to do this, right? We take our original matrix, we subtract lambda. Let's do it with fractions. So we have 1/4 minus lambda, 1/3, 3/4, and 2/3 minus lambda. So we get 1/4 minus lambda times 2/3 minus lambda minus 1/4 is equal to 0. Lambda squared minus, so 2/3 plus 1/4, fraction, so minus 11/12 lambda, and then 1/4 times 2/3 minus 1/4 as a fraction, minus 1/12 equals 0. I know 1 is going to be 1, so the other one has to be plus 1/12, which I see works. So I get lambda equals negative 1/12 and 1. If I do lambda equals negative 1/12, I get 1/4 minus negative 1/12 or plus 1/12. That's going to be 1/3, 1/3, 3/4, 3/4 acting on xy is equal to 0, 0. That gives me 1, negative 1. And lambda equals 1. 1/4 minus 1 is negative 3/4, 1/3, 3/4, negative 1/3. Acting on xy gives me 0, 0. Negative 3/4 x plus 1/3 y is equal to 0. Multiply top and bottom by 12. Negative 4 by 12. Okay, so if you multiply by 12, you get negative 9x plus 4y is equal to 0. And that gives me 4, 9. So T is equal to P, my matrix of eigenvectors, times D, my matrix of eigenvalues, times the inverse, which I get by flipping, negating, and then dividing by 13. So I'll put a 1/13 in front. So that's part C. Part D. Show that T to the N equals this simplified form. So T to the N is 1/13 times 1, 4, negative 1, 9, negative 1/12 to the N, 0, 0, 1, 9, 1, negative 4, 1. Which equals to 1/13. So I get negative 1/12 to the N, negative of negative 1/12 to the N. Is that correct? Yeah. 4, 9 times 9, negative 4, 1, 1. So this gives me 1/13 times 9 times negative 1/12 to the N plus 4. Negative 9 times negative 1/12 to the N plus 9. Negative 4 times negative 1/12 to the N plus 4. And positive 4 times negative 1/12 to the N plus 9. So what I'm getting is not what they're getting, but either I'm working too quickly and I'm making a silly mistake somewhere, which I'll certainly check afterwards, or they're wrong again. But let's assume this is correct. E. Hence, find an expression for the number of customers buying from R after n years. Well, if I want the number of customers buying from R after n years, all I have to do is to apply t to the n to my initial state vector and read the top row, because I'll have a vector, my state vector, R and S. So I'm not even going to write it because I'm just be copying it over. It's just t to the n times S naught. F, verify your formula by finding how many customers are purchasing from R for 2 years. Okay, well, I can certainly do this one and see if my answer or their answer is the correct one. So now that I have my t squared, I'm just going to plug it in. 9 over 144 plus 4 divided by 13. That gives me 0.3125. And negative 9 over 144 plus 9 divided by 13 gives me 0.6875. Negative 4 over 144 plus 4 divided by 13 gives me 0.305 bar. And 4 over 144 plus 9 divided by 13 gives me 0.694 bar, acting on S naught, which was 6,500, 5,200. And these numbers certainly look familiar from above. 0.3, yeah, 0.3125, 0.6875, 0.305 bar. Hello, they're wrong again, and I'm right, yeah. Anyways, G. Find the long-term number of customers buying from R, T infinity. Well, it's going to be 1 over 13, 1, 4, negative 1, 9, 0, 0, 0, 1, 9, negative 4, 1, 1. So 0, 0, 4, 9, 9, negative 4, 1, 1. This gives me 4, 9, 4, 9, or 4 over 13, 9 over 13. So the long-term number who's going to buy from R is going to be 4 over 13 of the total amount. Well, what is the total amount? The total amount is 6,500 plus 5,200, which is 11,700. I think I wrote that down. What I didn't, but it's okay. And when I multiply that by 4/3, so therefore the answer is 4/13 of 11,700, and the answer is 3,600. So in the long run, we expect 3,600 to be bought from R. And this takes us to the end of the eigenvalue, eigenvector section. I hope you had a lot of fun with it. Some really cool stuff. Next, we will move on to graph theory. Yes, I will see you there. Bye.